Hello.
That's working.
Mine's on. That one's on.
Cough. I'll just scream. Hey everyone, can I have your attention?
This one goes this far.
We don't have a microphone today, but in terms of SI sessions, there's one tonight. The SI session tomorrow, I'll erase it, it's canceled, okay? The polls are open from 6:30 a.m. till 7:30 p.m. So we're canceling the session tomorrow, so hopefully you guys can do what I'm going to do, which is go vote. So session tomorrow, Tuesday, election day, canceled. Or if you're from Ohio, it's election day.
Tonight SI session talking about buffers and theory about them because it's another theory day, and going over the exam. So if you want to do any of that, you should come.
That it? You think so? Okay. If you haven't been online lately, yes, the scores are posted. The only reason they didn't get posted sooner was I was lazy all weekend. I don't think there's anything wrong with the test. In other words, you're going to have a heart attack. So, very normal, right? Here's what I can tell you is that 6 of you scored 99 or 100. 3 99s and 3 100s. There are 17 of you with scores of 40 or below. Those 17 people may want to rethink how they're approaching the class. The medians, or the mode, as you can tell, is 72. There's 13 people with a score of 72, so statistically you're right there. The median score was 73. So if you rank them top to bottom and go to the middle of the pack, it's 73, and the average was 71.4, I think, 71 point something. So all 3 of them are right there, 72, 71, 72, 73. So it's a pretty normal distribution. You can see it's relatively flat from about 70 up. It doesn't look at all out of line. I always shoot for a 75. When the semester is done, when you figure in all of the grades, I shoot for a 78 to 82. When you figure everything in, right about 80 is the class average. But the test average ends up being somewhere around 75. So is this number lower than I'd shoot for? No, it's about in line. But as you can see, it's pretty heavy on the top. It's the 40 scores below 14 are pulling that average down quite a bit. And that doesn't include any zeros. Those of you who brought me your exam in an envelope, they're not in here yet. The TAs I couldn't find them to give them the test, so there's about 6 of you that need your scores posted still. So you know who you are. I'll have those for you Wednesday. So questions? All right. Let me get rid of this. Blank screen, PC, blank screen again. Shut this off. I have no idea why this thing won't go off for me. There we go. All right. Yep, lights, camera, you know, the whole 9 yards. I do have the exams for you. We'll hand them back at the end of class. We're going to start with 50 milliliters of 10th molar nitric acid. Okay? So we're going to start with a strong acid, start with 50 milliliters of it, and I want you to calculate the pH for 7 different solutions. And before you sit there and say, oh my gosh, that's an heck of a lot of calculations, there's going to be a lot of redundancy here.
Is 1 really 0 milliliters?
I'm sorry?
Is it 0 milliliters?
Yep, 1 is actually 0 milliliters of NaOH. So that first one you can all tell me the answer to right now, right? What is the pH of 50 milliliters of 10th molar NaOH? Or some of you can tell me the pH of that. I heard it over there. I'm sorry? 1. So the first solution where all you have is strong acid, the HNO3 falls apart into its ions. You've got H plus and NO3 minus. The concentration of H plus is going to be equal to the concentration of the acid. It's 0.1 molar, which is 10 to the minus 1. The negative log of that, the pH is going to be 1. That for extra M was a mistake. So, first one, pH is 1, if you want 1.00. When I add 15 milliliters of strong base to it, should the pH go up or down? Up. It has to go up. You're adding base to it. The pH has to go up. Okay? Anytime you add a base to an acid, the pH will always go up. The question is, how much will it go up? This is a limiting reactant problem. If you approach a titration, which is what this is, as a limiting reactant problem first, followed by an equilibrium, ooh, that sounds familiar, then you will be able to solve these problems. But do the limiting reactant problem first. Okay, if we need a limiting reactant problem, we need moles. So how many moles of hydrogen HNO3 do I have? Well, I've got 50 milliliters. We're going to make the calculation nice and simple. We've got 5 millimoles of HNO3. 50 milliliters times 0.1 molar. So in solution number 2, you have 1.5 millimoles. So what's my limiting reactant? Sodium hydroxide or HNO3? Sodium hydroxide, it's a nice 1-to-1 reaction. The nice thing about most acid-base reactions is they're 1-to-1, so we don't have to worry about balanced equations. H plus plus OH minus gives me water. So I've got 1.5 millimoles of sodium hydroxide. I've got 5 millimoles of HNO3. So what do I have? I use up the sodium hydroxide. How much HNO3 do I have left? The excess HNO3 is the amount we started with minus the amount we reacted. Everybody with me so far? I haven't lost anybody yet. Now I want the concentration. Number of moles divided by number of liters. Because we're doing it in millimoles, it's a simple way to do this calculation. I just have to divide by milliliters, and the 2 millis cancel each other, so I have moles per liter. How many milliliters of solution do I have? I've added 15 milliliters to 50 milliliters. So I've got 65 milliliters. What'd you get, Jeff? I'm sorry? 0.05. So it's 0.05 molar HNO3, which makes sense. It was 0.1. We've neutralized it. And so the concentration, did it really get cut in half? 3.5. Yeah. 0.054, okay. I'd rather go one more digit. All right, so the pH of that second solution now isn't too bad. 1.27. Boy, chalk is dry today. 1.27. So the pH did indeed go up. It didn't go up very much, but it did go up. Okay, add 15 more milliliters. When you approach this problem now, there's two ways to do it. And I always forget that to me it's automatic to do this. To you it might not be. I'm just going to add 30 milliliters of NaOH to that first solution again. It's a much quicker way to do this than to worry about the fact that I even did that second step. So if I do the, for solution 3, I started way back in the original solution with 5 millimoles of HNO3. That doesn't change for this whole problem. And the number of millimoles of base added is 30 milliliters. So I've got 3 millimoles of base that I'm adding, the excess acid, that's the limiting reactant part of this problem. I use up the base. Now, before I go too much further, does everybody see what I did? I've just neglected step 2 completely. I said, okay, if I started with that first amount of stuff and I add 30 milliliters of base to it, this is what's going to happen. If you had wanted to do it the other way, it would work out to be the same way, but it's easier just to go all the way back to the first solution. You're still adding it to the first solution. So you've got 2 millimoles of excess HNO3. The concentration now what do I have now? I've got 50 milliliters plus 30, 80 milliliters. Okay? So the concentration of nitric acid keeps going down as it should. I'm diluting it and I'm neutralizing some of it. And the pH, I'm sorry? 1.6. So again, the pH is still climbing. The change in pH between solution 2 and solution 3 is a little bit greater than it was between solution 1 and solution 2, but it's still pretty flat. It's not changing a lot. If I keep going in solution 4, 45 milliliters. Well, I can probably skip a step now, right? In solution 4, if I've added 45 milliliters of NaOH, it's 0.1 molar. That's 4.5 millimoles of NaOH. I started with 5 millimoles of acid. So the excess acid is 0.5 millimoles. Hopefully everybody can see that part. So we've got 0.5. The concentration. Now I'm up to 95 milliliters of solution. I started with 50. I've now added 45 more of base. Give me one more digit. 0.0053 molar. Without a calculator, can you tell me what the pH is? There's a hint. Right there. It's 1 power of 10 different. How close am I? 100th? 0.28? I'll live with it. So the pH is about 2.27. Have I lost too many people yet? So far it looks pretty easy, right? It's a strong acid with a strong base. The calculation's pretty straightforward. Once you see the first one, they're all done exactly the same. So, solution 5. So I start with 5 millimoles of acid initially. I add 49 milliliters, I think I said, of NaOH. So I've got 1 millimole, or 0.1 millimole. Of excess acid that hasn't been neutralized yet. The concentration. Zero, 1, 1. It should be 0, 0, 1, thank you. I was going to say the pH isn't going to be right. So the pH of this solution now is 3, right? Is it 4? Okay. You probably did 3 zeros. All right, solution 6. Now I'm really going to take a shortcut. I'm not even going to subtract out the base. Hopefully at this point you can see I'm just taking 5 millimoles times whatever the milliliters times the concentration to figure this out. So the concentration of HNO3 is now (1 times 10 to the negative 4). And so the pH at this point is 4. Solution 7. No calculation required. What's the pH? 7. You're at the equivalence point. You've added an equivalent amount of acid to the amount, or excuse me, equivalent amount of base to the amount of acid you started with. You started with 5 millimoles of acid. You've now added 5 millimoles of base. You've completely neutralized the acid. You've just got water. The pH will be 7. So solution number 7, the pH is 7. So if you look at this, and you make a plot, one of my complaints about Chem 113, by the way, is you never make this plot. And it would help tremendously, I think, if you did. You did have to do it in pre-lab? You had to calculate all the pHs? I didn't think so. I've never seen this plot. That's what bothered me. But if we take this one, we started at a pH of, way up there, 1. And the pH climbs relatively slowly until we're at the equivalence point. The equivalence point, as we said, is where you've added an equivalent amount of base to the amount of acid you started with. And now on the other side of this, for a strong acid and strong base, it's going to be symmetrical. If I go 1/10 of a milliliter past the equivalence point, if we go backwards now, the pH will be 10. It'll be 3 pH units different than where I am at the equivalence point. If I go 1 step beyond that, the pH will be 11. So now I'm just working backwards. 7 minus 4 gave me a 3 pH unit change from here to here. When I go the other side, I'm going to get another 3 pH unit change. When I go the 9/10 of a milliliter beyond that, I'm going to get yet another pH unit change. So this curve is very symmetrical, and it looks like that. Every single strong acid, strong base titration will look like this. It's a very steep. If you take the derivative of this, you can do this in your calculator. It's great. You've got your graphing calculators. Once you get it in there, take the derivative of this. What does it look like? Well, the derivative of this curve looks like that. You've got a huge change in slope in this region right here, and then it comes back the other way. This should be lined up exactly. I have it offset a little bit. So where this peak is exactly the equivalence point. So if you can plot it in your calculator, it will tell you the value. You can use the trace function to follow this. This is, those of you who did titrations in high school, you used an acid-base indicator to determine where the TH changed. And the one you probably used was phenolphthalein. Phenolphthalein, if you want to get some, just go to the grocery store and buy X-Lax. It's the main ingredient in X-Lax. So is it harmful to drink that stuff in lab? You won't like the results, but it won't kill you. But the nice thing about phenolphthalein, and the reason why it's usually used for your first titration, is because the color changes from colorless to pink. And it changes color in a range of about 8.6 to 9.4. Every single acid-base indicator that you will use is itself an acid or a base. And it changes color at a point where it converts from the acidic form to the basic form. Phenolphthalein changes color at about pH 8.2 is where the conversion is complete. What indicator you pick depends upon its use. We'll talk about which one in a second. So this is a strong acid with a strong base. What if I start with a strong base and add a strong acid to it? It's just the opposite curve. You start at a high pH, you get this nice symmetrical, very sharp curve, and you end up at a low pH. So that would be starting with a strong base and adding a strong acid to it. Now, let's complicate it. Let's not make it nitric acid. Make it acetic acid. Now you've got a weak acid. It makes the calculations much tougher. Why? The reaction of nitric acid plus sodium hydroxide produces water and sodium nitrate as products. That's the molecular equation. The net ionic equation is that one. Because sodium nitrate is a soluble compound, it's 100% electrolyte. It dissociates into its ions. So I have sodium ions on the left side of the equation, I have sodium ions on the right, so the spectator ions cancel out. I have nitrate ions on the left, I have nitrate ions on the right, they cancel out. So that's the net ionic equation. It's pretty simple. Acetic acid is a little tougher. Now we've got a weak acid with a strong base. We get sodium acetate, which is still an aqueous compound. with water, which is a liquid, but the net ionic equation this time has to keep the acetate ion in there. Thank you. So the acetate ion has to stay in the reaction. Acetic acid is a weak acid. For a net ionic equation, if something is a weak electrolyte, you don't dissociate it into its parts, only strong electrolytes. So I've got the acetic acid that's going to give me acetate ion. This is an acid. This is a base. When I add sodium hydroxide to this reaction, I'm making a base in the process. So over here, where I was able to just subtract things out, it was a piece of cake. When I do it with a weak acid, I have to add in one more thing. So let's try it. Most of these calculations will stay the same. Initially, you'll see the change. Solution number 1. I've got a weak acid. I'm not even going to worry about, there's no sodium hydroxide yet. I don't have to worry about it. But I have to solve the equilibrium. And we're going to do it exactly as we've done all these others. Whoops. Thank you. So we solve this first equilibrium. And every step on the way, we're going to have to solve an equilibrium. The Ka for acetic acid is 1.8 times 10 to the minus 5. This is exactly like the first weak acid equilibrium we did. It's probably exactly the same solution. So we make the assumption. So we get x is equal to the square root of 1.8 times 10 to the minus 6. I brought the point 1 over. That's why the number changed. One more digit. 3. Thank you. 1.3 times 10 to the minus 3 sounds right. That's the hydrogen ion concentration. And so the pH, .87. It's almost 2 orders of magnitude, 100 times less concentration of hydrogen ions as for HNO3. So on our titration curve that we have there, we're going to start at a higher pH if we've got a weak acid than we do if we have a strong acid. Okay? Now add 15 milliliters of sodium hydroxide. As we said Friday, approach these problems as a limiting reactant problem first and an equilibrium problem second. The nice thing is the number of millimoles of acid doesn't change. I still start with 5 millimoles of acid. I'm going to add the same amount of sodium hydroxide, 1.5 millimoles. So far, nothing's different. The excess acetic acid is exactly the same. The concentration of the acetic acid is going to be exactly the same. I don't remember what the number is, Jess. How much? So far, everything looks exactly the same as before. So now I just have to solve an equilibrium, except for one thing. When I neutralize the acid with the base, I make base. So I also have to figure out how much base did I make. So how much base is there in addition to acid? Anybody know how many millimoles of base there are? Jess does. How much sodium hydroxide did I add? 1.5 millimoles. How much base did I make, therefore? 1.5 millimoles. For every mole of strong base I add, I make an equivalent amount of weak base. So I've got 1.5 millimoles of acetate ions. And the concentration is 0.2. Now I've finished the limiting reactant problem, and I still have an equilibrium problem to solve. The reason I emphasized limiting reactants so much last semester is because hopefully now that we're doing this, limiting reactant problems are a piece of cake for you. They make complete sense. The nice thing is it's a one-to-one reaction, so we don't have to worry about if there's 3 moles of this and 2 moles of that. It's going to be one-to-one. It's going to simplify it a little bit. Make it so I can reach. So now that we've got this set up, and now the solution that I have to figure out the pH of starts with acetic acid, starts with acetate ions. There's no H3O+. So we fill out the equilibrium table. Now we solve it. Wait, did I do it right? How much? Should the pH go up or down, by the way? You added base, pH has to go up. That will never, ever be violated. pH will have to go up. This is now, if I go back and look at my table, my hydrogen ion concentration. So my pH is 4.37. Nope, I don't have to take a square root, because I'm going to assume that x is much smaller than this. So if that's the case, then this becomes 0.023, this becomes 0.054, and I just have 1x. So I don't need a square root. All right?
Why are you using that equation and not that?
Why am I, okay. The question is, why am I using this equilibrium reaction instead of this reaction here? We already used this one, right? This was the limiting reactant part that we did first. Once the limiting reactant is figured out, you don't need that equation anymore. So we have to do the equilibrium then with what's left. That's why, and it is the hardest part about understanding what a buffer is. Every single buffer works the same way. As we defined Friday, a buffer is a solution where you've got weak acid and its conjugate base in relatively equal amounts, and they will resist changes in pH when you add acid or base to it. Is the solution I started with a buffer? I started with 10th molar acetic acid. Is it a buffer solution? No. Why not, Thomas? There's no conjugate base. You have to have an acid or base and its conjugate in relatively equal amounts before you get a buffer. Notice what happened when we added 15 milliliters of sodium hydroxide to this. The pH went from a pH of 2.87 to 4.37. It changed by 1.5 pH units. That's a 150-time increase. That's a huge change. It's definitely not a buffer. But now look at what we've got. We've got a solution that has 0.05 molar acetic acid and 0.02 molar acetate ion. What do you think is going to happen when we add base to this? If it's starting to behave like a buffer, the pH change should get smaller. When we add 15 milliliters to this, look at the pH change. So compare solution 2 and 3 when we did the strong acid plus sodium hydroxide, and then when we finish this one, compare it to it. Okay? I'm going to quit there for today, but try this. Try figuring out the pH of solution 3, right? And see what happens to the pH. We have your tests. We'll split them in thirds. Give us just a second.